Hello students, this lesson is called Devising Half Reactions with and without oxidation numbers. So quick review, remember with oxidation numbers the magnitude of the change indicates the number of electrons lost and gained. If the oxidation number goes up, like if the rocket goes up, we've lost the electrons, we've lost it. Elon Musk invented a rocket that could land vertically. I'm showing a parachute there, that was in the old days. If we get the rocket back, if the oxidation number goes down, we've gained electrons. And a change in oxidation numbers indicates if a reaction is a redox reaction, like that one. Zinc's oxidation number changes from 0 to +2, or sorry, manganese changed from +2 to 0. So there's a change in oxidation number, and therefore that is a redox reaction, which just means there's electrons lost and gained. Some substance is losing electrons, the other substance is gaining electrons. And the magnitude of the change indicates the number of electrons lost and gained. So when I change from a 3 to a 2, that means I'm involving 1 electron. When I change from a 0 to a +4, I've lost 4 electrons. Okay? All right. And disproportionation is when one substance acts as both the OA and the RA. So if you look at oxygen, the oxygen appears to be going from -1 to -2. Okay, so if the oxidation number goes down, looks like my picture's in the way there of my face, but if the oxidation number goes down, we've gained 1 electron, which means we've been reduced. Okay, so it's reduced, we're the oxidizing agent. But also, if you look, oxygen's also going from a -1 to a 0. So when the oxidation number goes up, we've actually lost electrons, oxidized. So that atom is both the OA and the RA. When one substance can act as both the OA and the RA, it's called disproportionation. Okay, when one substance acts as both OA and RA. Okay, all right, now to the heart of the lesson here. We're going to devise half reactions. So we're going to give you an incomplete reaction and we're going to create the rest of it, or devise it. Okay, so we're going to start with doing this with oxidation numbers, which is the preferred method in my class. Okay. So here's the rule. So here's our skeleton. We haven't fleshed this out yet. So we're going to start with Cr2O72 negative turning into Cr3 positive. First rule, balance the atoms that are not O's and not H's. Okay, so I don't care about the O's. There's 7 of them, but I don't care right now. 2 Crs, put 2 Crs over there. Next one, I want to assign oxidation numbers and add electrons. The appropriate number of electrons. So the O is a -2, so Cr is a +6 because it has to equal -2, and that Cr is a +3. Cr3 positive is +3. Okay, now let's take a look. My oxidation number is going from 6 to 3, so I've gained 3 electrons. If my number goes down, I gain electrons. On a per atom basis, look at it like this. I have, that structure doesn't look exact, I'm just being simple here, but I've got 2 chromiums attached to those O's. My oxidation numbers are telling me that for every 1 chromium I gain 3 electrons. So if there's 2 chromiums, each one's gaining 3, but I'm gaining 6 total. Okay? So I'm really gaining 6 electrons total, 3 per atom. Okay, next, I'm going to put my electrons in. So whenever we're gaining electrons, we put them on the reactant side of the equation. Okay, and now I'm going to, recall that when electrons are gained, they are placed on the reactant side. If they're lost, they go on the other side. Okay, now I'm going to add water to balance O's. So there's 7 O's, there's 7 waters. Because when I add water, I've added 7 O's. So now I got 7 O's on both sides, I'm balanced. Now I'm going to add H positives. 14 H's there, so I got to put 14 H positives on the other side. And now my equation's actually balanced. I can check my net charge to see if it balances, I say, electrically. So I got 14 positives there and -2 there, so I'm at positive 12. Another 6 negatives brings me to positive 6. On this side I've got a positive 6 because I have 2, 3 positives, and 0. Oh, my picture's in the way there. Can I hide myself? No, not once I start. Okay, and that adds up to +6 on that side and +6 on that side. They have to be the same. They don't have to be +6 every time. It could be -4, -4, +2, +2, but they got to be the same. Okay, good. Now I'm going to show you the other method. This method does not use oxidation numbers. I don't prefer this method. I kind of use it as a backup in case for some reason I can't figure out the other question. But it's really important to use oxidation numbers because you need to know oxidation numbers for other things. So the other method forces you to do oxidation numbers, which forces you to know oxidation numbers. But if you got stuck, we start the same way. Balance the atoms that are not O's and H's, so I don't care about the O's. 2 CRs, done. Add water to balance O's. I got 7 O's there, so I add 7 waters. I got 14 H's, so I put in my 14 H's. And now I check the net charge. Now my video might be in the way here, but I check the net charge. On this side, I've got a +12. On that side, I got a +6. Remember, electrons are negative, so I've got to put my negatives in. Where would negatives go to get me to the same number on both sides? Well, if I put 6 negatives over there, that's going to reduce me down to +6 and +6. So there's your answer. Okay, all right, that's how to balance, that's how to create half reactions, devising half reactions. Okay, see you next time.